So today we will see how we can write input script for lamps. So to write the input script for lamps, I will be using the example of argon gas. So before writing the input script for lamps, it's very important to have an idea of what type of system you are going to study. Okay, so either you are going to study solid, you are going to study liquid or gas. So I am using argon gas here. So with the help of example of argon gas, we will see how we can write the input script as well as various type of keywords that are used in lamps. So to have an basic idea of how we can start writing our input script for various type of systems that we can study. Okay, so the first step is to create a simulation box. Okay, so this is a box that is going to contain the atoms, and that atoms are going to interact with each other. So the first step is to create a simulation box. So the first line that I am going to start with is dimension. You can see here it's dimension and 3. So what does this mean? So this means that the simulation box, or you are uh, running your simulation in 3 dimension. Okay, you can also do simulation for simulation in 2 dimensions or in 3 dimensions. So if you want to do in 2 dimensions, so here I will remove 3 with 2, and it is in 2 dimension. But if I remove it with 3, or if I don't write anything here, then the default dimension in lamps in 3D is 3 dimension. Okay, I hope this is clear. Now the next what I want to define is the units of the quantities that I am going to use in the input script. So whatever physical quantities that I am going to use in the input script, like the position, unit of length, unit of velocity, temperature, pressure, kinetic energy, potential energy, whatever it is. Okay, so this is done with the help of units keyword, and I will take you to the lamps documentation. So here if I write units metal, so this is the syntax of a unit command. Okay, so units is the keyword here, and this is style. So style could be LG style, real, metal, SI, CGS, electron, micro, nano, whatever it is. And so if you see in my input script, I am using the metal style here. So what does this mean? This means that if I you can see here, okay, this is the metal style. So in case of metal style, these are all the physical quantities that are that we can calculate, or that we will define in our system. So mass will be in grams per mole, distance will be in angstroms, time will take the unit of picoseconds, energy will take electron volt, similarly pressure will take bars, and temperature will take Kelvin. Okay, so these are the units in case of the style metal. And you can also use other units like real, then the other things will change, like time will go to femtoseconds from picoseconds. Okay, otherwise you can use SI style, you can use CGS style. So every style has its different units. So after unit, it is the now boundary condition. We have to define the boundary of our simulation box. So I have written here P P P. So these are the boundary conditions for our simulation box in 3 sides. Okay, we have 3 sides, X, Y, Z. So p mean periodic here. If we look at the syntax of this, I will type boundary here. So this is the syntax of boundary x, y and z. So this is you can write either p, s, f, m, or whatever you want to do. So p is for periodic, f is for non-periodic and fixed, so s is for non-periodic and shrink wrapped. Similarly m is there. Okay, so what I am going to use is a periodic boundary condition. So why I am going to use periodic boundary condition? The simple idea is there that whenever I am going to study our system, so I have a simulation box which is containing some number of atoms. Okay, so if a atom leave out of the system at the boundary, then if I have a periodic boundary condition, then the same atom will enter in the simulation box from the another side. So what I want to do, I want to keep the number of atoms inside the simulation box constant. I don't want them change during the time period of simulation. And another thing is that we want to avoid any kind of surface effect that can happen if we don't have any periodic boundary condition. So this is the, you can also use other kind of boundary conditions. It is given like, it is given here like ppf, pfsp. So whatever your simulation box, your input script demand, on that basis you can choose it here. Now I will move to the next. This is atom style. So atom style is atomic here. So basically what is atom style? Actually it tells you what quantities the atoms will store. Okay, what quantities are stored by each atom in our simulation box? Now in this case the various quantities will be velocity, position, atom IDs, various type of atoms, like this. So why do we need them? Velocity, position, atom IDs? Because this is the basic foundation of molecular dynamic simulation, where these are the microscopic properties that are used to calculate the macroscopic property of the system, like pressure, temperature, volume, or energy, whatever you want to calculate. Okay, and I have defined these things, everything, in other videos that you can see on my channel. After that I will create the simulation. I have defined the various parameters for my simulation box. Now to create my simulation box, first it's very important to define the lattice structure of my the system that I am going to study. Now I am studying argon gas, so lattice is the keyword here, and abscissa is the structure of crystal structure of argon, and this is the lattice constant 4.58. And you can also check it on LAMMPS documentation by yourself. Now the next command is the reason command. Okay, and this is the reason. And okay, let me take you to the LAMMPS documentation. So this is the reason command here. Okay, so this is the keyword reason, and after that this is the id. Okay, so id is user assigned name for the reason. Okay, whatever you want to give it, so I will give it my reason, that is a user assigned. And what kind of box that you are going to use, or you want in your system. So it can be a block, it can be a cone, it can be a cylinder, plane, prism, sphere, or whatever you want to do. Okay, so I have taken here it is a block, and these are the corresponding dimensions of block. So 0 10, 0 to 10, 0 to 10, this is for x direction, this is for y, and this is for z direction. Okay, so you can see here this is block, and these are the arguments is x low, x high, y low, y high, and z low, z high. So these are the bounds of block in all dimensions. Okay, so the default unit will be the lattice here. Okay, what does that mean? That what will be the actual size of your simulation box? If you see, what will be the size of your simulation box? So it will directly multiply the lattice constant with these values. Okay, so the minimum, it will start from 0, and the maximum it will go to 45.8. 4.58 multiplied by 10 is 45.8. Similarly, 45 point high value or maximum value of y is 45.8, and maximum value of z is 45.8. So it is simply multiplying this by this, and this is the size of our simulation box. After that, creating the region, now I will create the box. Okay, so create box is the keyword here. Now let's go to the LAMMPS documentation page. Okay, so this is the syntax for create box command. So this is the keyword create underscore box. After that there is n. So it's a hash of atom types to use in this simulation. So what does this mean? This mean actually how many types of atoms you are going to use in system. Like in my case, I am going to use argon. So there is only one type of atom. If you if I am using argon and another atom, say krypton. Okay, so there are, I am studying a system of argon and krypton. So in case of one, I will write 2 here. Okay, I will write 2 here, but I am using only argon, so I will write here 1. Okay, and after that there is the idea of the region. So what is the idea of region? This is the idea of my region, that is my region. Okay, after that I have created the box. Now I have to fill the atoms in the box. So atoms are filled in the box with the help of create atoms command. Okay, so let us see the syntax of create atoms command. Okay, so this is the syntax of create atoms command. This is create atoms, this is the keyword here, and now type. Okay, so atom type of atoms to create. Now what does this mean? This means that which kind of atom you are going to fill in your box. Okay, so now I have only one type of atom, that is argon. Okay, so I will write here 1. Now let us say that I have also krypton atoms in the simulation box. So what I will do, I will after writing this command, I will write another command of create atoms, and I will fill the krypton atoms in the same simulation box by writing 2 here. Okay, so I will write another command of create atom, then I will write 2 here, but only I am using a single type of atom, that is argon, so there is no problem with this, so I will use only 1 here. Okay, and this is followed by the style. Okay, so what is the style? So either box, region, single, and random. So I am using the region, and after that I will give the id of my region. Okay, and the name of region id is my region actually here. Okay, so this is the uh, so in these lines our simulation box has been created. Okay, so simulation box has been created, as well as we have filled the atoms, the simulation box with argon atoms. Okay, now after this I will define the mass using the mass keyword here. One is only one type of atom, so its mass is going to be 39.948. And what will be the unit of 39.948? That we can check from the unit metal command. Okay, I think it was in grams per mole, something like that. Let us check it. So mass, yeah, grams per mole. Okay, so in case of metal it is grams per mole, so it will be equal to 39.948 grams per mole. Now we will see what is interaction potential. So as you have created the simulation box and you have filled the atoms in the simulation box, now the atoms are going to interact with each other. Okay, so how atoms are going to interact with each other, it is always defined by the interaction potential. So different type of elements may have different type of interaction potentials. If I talk about noble gases, so mostly the Lennard-Jones potential is used. So how the syntax is written, we will see here. So this is the keyword pair style that is used to write the interaction potential. So we will write pair style. After that, okay, let me take you to the LAMMPS documentation command. So it is pair style. So we can have different type of pair styles for a liquid, for solid, for a gas. Okay, so in case of noble gases like argon, we mostly use the LJ potential. Okay, so this is the syntax. This is pair style. This is the keyword, and now the style comes here. So style could be one of the style from the list below. Okay, so there is the list. This is a very big list, and here you have to choose your interaction potential, which interaction potential that you are going to use. So I am going to use LJ cut, is a cutoff Lennard-Jones potential without column. So what does this mean? So this is LJ cut and this is 10 here. So 10 is basically the cutoff distance. So the distance will take the units of angstroms as specified by the units metal. And what does this mean? That if the distance between any two atoms is more than 10 angstrom, then there will be no interaction between them. But up to the distance of 10 angstrom, there are going to be interaction between any two atoms. Okay, uh, let me tell you another thing is that LJ potential is a two body potential. So the interaction between two atoms is always depends upon distance between them. It is not affected by the presence of any third atom. Okay, now next come the pair coefficient keyword. So what is the pair coefficient keyword? So I have made a video of Lennard-Jones potential, and if you see that video you will see that we have uh, we have in the formula of Lennard-Jones potential we have sigma and epsilon, that are the unit of energy, and the unit of sigma is the unit of length and epsilon is the unit of energy. And we have to define both sigma and epsilon in case of our interaction potential. So pair coefficient 1 1, so it is the interaction between the types of atoms. So I have only one type of atom, that is argon. So both my atoms will be argon, so there will be interaction between argon. Okay, and this is the value of sigma, which is the unit of length, and this is the value of epsilon, which is the unit of energy. And what does this mean? I have created a video on Lg potential. You can see that video and learn about Lg potential. I have stated there in a very clear manner what these values actually mean. Okay. So now after defining the interaction potential, I will perform the minimization. Now what is the role of minimization? Why do I need to perform the minimization? It's actually, let us say that you fill your simulation box with the atoms at any random positions. Okay, now the system initially may have at high energy. Okay, so we want our system to be at minimum energy so that we can start our simulation work. So minimize is the keyword here. So there are the first value is is the tolerance. Okay, this is energy tolerance, this is tolerance for force. So what does this mean? That when the distance between when the difference between any two iterations in case of energy or in case of force is equal to this distance, then the minimization will stop. When the difference between any two iterations is equal to this is for energy, this is for force, and this is the number of iterations that you want to perform this. Okay, so I want to perform it for 10,000 iterations in both in case of energy and force. So when, and also the minimization will stop when the steps or when the iterations will be equal to 10,000, automatically the minimization will stop. So these are some criteria for minimization to stop. Now now this is a time step, this is 0.001. I will tell you the use of this later in this input script. Okay, now the next step is to, now we have filled the atoms in the simulation box. We have also defined the interaction potential, that how our atoms are going to interact with each other. Now our atoms are not moving. I already told you that what is the basic of molecular dynamics simulation is, we want to create, or we want to find the position and movement of the particle with the time evolution. Okay, so what we will do, so we will provide some initial velocity to the atoms by setting the temperature of our system equal to 400 Kelvin. Okay, so how it is done? So we will write here velocity, this is the velocity keyword. So let me take you to the LAMMPS documentation. If I write velocity here, so I have the velocity command, here, and the this is the syntax of velocity command. Okay, so this is velocity and this is the group ID. So what is the ID of my group? So in this case I have not defined any group in case of my input script, so I will write all here. So all means it will take all the atoms in the simulation box. Okay, it is not going to choose. If I have any different types of atoms, say argon, krypton, and I want to provide the velocity for some specific type of atoms, so I will then create group for different types of atom. But here only I have one type of atom, so I will write all here. And after that, style. Okay, So I'm going to use the create style here. So this is the create style and these are the arguments with create style. So this is the value of temperature. So this is the value, this is create and this is the value of temperature. Temperature will 400 and it will take the units Kelvin, and this is a random number. Now why I am giving the temperature of 400 Kelvin here, because temperature is directly linked with the kinetic energy. Okay, so if I give some temperature to the system, so the atoms will acquire some velocity, so that, and the velocity they will acquire in such a way that the temperature of the system is equal to 400 Kelvin. And whenever we want our system to remain in thermal equilibrium, so we distribute the velocity among different atoms in our system in the Gaussian manner. Okay, so this distribution will be Gaussian, and these are the other keywords that has been used here, uh, that you can check. It's it is what it is. It is MOMS ROTS. So these are some keywords that you can, yeah, this is here. So keywords, these are the keywords used by create. If MOM is equal to S, linear momentum of the newly created ensemble of velocity is zeroed, and if rot yes, then angular momentum is zeroed. So this is the certain conditions that you want in your simulation box in your system. Okay, so I uh, I hope you have understood the role of velocity command here, that we will provide some temperature to the system, and on the basis of that the atoms are going to acquire some velocity, and if they have some velocity they will have some kinetic energy. Now comes the most important command in LAMMPS, is the fix command. So as I already told you that the basic foundation of molecular dynamics simulation is the classical form of statistical mechanics, in which we integrate the equations of motion to update position and movement of the particles in the system, or atoms in the system. So what happens if I don't use the fix command here? So atoms in the system are not going to move. Okay, so it's very important to move the atoms in the system, so that we can calculate their position and velocity with the time evolution. So if you see the syntax of fix command, so there is a fix, then comes the id. So this is a user assigned name for the fix. I have given it 1, and followed by the group id. So what is the group id? I have not defined any group, so I will simply write all. So it will contain all the atoms in the system, and then comes nve. So nve is a style. So you can see here the nve style. This is NBE style, so it represents the constant NBE time integration. So what does NBE mean? It means the number of N mean number of particles in the system, V is the volume of the system, and E is total energy of the system, that is going to remain constant. Okay, so it will remain constant throughout the simulation NBE. Okay, and after that I will use the dump command. So what is the use of dump? So it is mostly used for visualization in Obito or other soft visualization softwares that are used. So it is a kind of output file, and I will show you how we can see our simulation box or our system in Obito later in this video. But initially, first let us look the structure of this dump. So this is the keyword, and if I go to dump command, so this is dump followed by the id, so it is user assigned name for the dump, and the name that I have defined is dump underscore one. Then comes the group, then I will write all for all the items in the system. Now I am using custom here. So why I am using custom here? So that what actually I want to uh, what information I want in the dump file, I am using custom. If I don't use custom, then lamps can use the default values, so it will store the default information in our dump file, but I will use custom. After that, it is 100 mean how frequently I want to print the information in the dump file. So I will put information in the dump file every 100 step. Okay, after that, this is the name of the file in which I will write my dump information. And now comes, this is the atom ID, this is the type of atom, and X, Y, Z are the positions of the atoms. IX, IY, IZ are the image flags, and VX, VY, VZ are the velocity of the atoms in X, Y, and Z direction. Okay, now comes the command thermostyle. So thermostyle command is basically used to print data in the log file. Okay, so what is a log file? Log file contain entire information of the system. So by using the custom, what I want to print in the thermostyle, I will use custom. Now I want to print step, I want to print the time, temperature, potential energy, kinetic energy, total energy, pressure, and the volume of the system. And after that it comes the thermo and 100. So how frequently I want to print thermodynamic information? Like in case of dump it was 100, in case of thermo I have also written 100. So every 100 step it will update all these positions. I will show you this in the log file. And now comes the command run. So run 5000 means that what actually the time, what is the time for which the simulation will run. So it will be equal to the time step I have defined here. This is 0.001. It is multiplied by the number of steps here equal to 5. So it comes equal to 5 picoseconds. So my simulation is going to run for a time period of 5 picoseconds, and after that I will so I will undump and I will unfix. Okay, so whatever uh, dump id I have created here and the fix id that I have used here, I have to undump it, I have to unfix it. Okay, now when you will run uh, this input script file, so what you are going to get, so this is the first file, that is the log.lamps. Okay, so log.lamps is a file that will contain entire information of the system. Okay, so this is the entire information of the system. So you can see here the size of simulation box. It has created a orthogonal box 000 to 45.8, 45.8 and 45.8. Okay, and it has created 4000 atoms. So, and this is the minimization that I already told you in the video, and this is the information that I have given in the thermostyle. Okay, so what I have given there, step, time, temperature, potential energy, kinetic energy, total energy, pressure, and volume. So you can see here, this is step, this is time, This is temperature, potential energy, kinetic energy, total energy, pressure and volume, and these are the corresponding values, and all of these have been updated after 100 times step. So first 100, 200, 300, 400. So this is what I have given here to print it after every 100 step. So, and that was the initial temperature, and now the temperature has been reduced to around 204 Kelvin. So the NBE, it is it all this has been done by using this command. Okay, using this command, fix one all NVE. So it is setting NVE is mostly used to make the system to reach the equilibrium. Okay, it is always used to make the system to reach the equilibrium. So that's why the temperature has been reduced with the time evolution. But that is not the point here. What I want to tell you, that how we can create the input script file in lamps, where we have studied about the various keywords. So this is, you can see here, this is the different color coding. I don't know what this color is, but actually all the keywords with the similar colors here are representing the keywords here that are default in the system. Okay, and and the next thing that I will show you, how you can visualize your result. So to visualize your results, this is the file, that is yt.dump. Okay, yt.dump. This is yt.dump. So this is the dump file that I have used here to store my information of position and velocity of the particles in the system. So this is Obito, and now we will see our simulation box in Obito. Okay, so this is our simulation box. So you can see here that the atoms are not moving, but as soon as I start, the atoms start moving. Okay, so this is because I have provided some temperature, and also I am using fix command to perform NBE integration. That why these atoms are moving. So this is basically the dump file. Okay, so the dump file is basically used, is a kind of output file that is basically used for the visualization in Obito. So with this, I hope everything is clear to you. But if you still have any doubt, please write your query in the comment box. And sorry for the background noise, because today it was not under my control. So really sorry for that, and thanks for watching. Thank you.